The night sky is filled with millions of stars. Each of these stars is a sun, and our own sun is one among billions in a sea of galaxies. It's hard to believe, but this big show has to end one day. Our sun will run out. But what about the entire universe? Will it come out on impact or disappear? Join us as we search for answers about the ultimate fate of everything. We will delve into the mysteries of dark matter, dark energy, and black holes to understand what drives the history of the universe. How will it all end? Planet Earth is located in a vast expanse of space that may seem modest at first glance, but upon closer inspection is very special. We orbit a simple star called the Sun, one of 8 planets in the solar system, which is itself part of a larger galaxy called the Milky Way. This galaxy, with its rotating arms, contains hundreds of billions of stars, many of which probably host their own planetary systems. The Milky Way is one of countless galaxies in the universe, each with its own unique assortment of stars and planets floating in space. The Sun, around which Earth and other planets revolve, is located in one of the spiral arms of the Milky Way, called the Orion Arm. About 26,000 light-years from the center of this galaxy, a supermassive black hole is a powerful center of cosmic activity that exerts a powerful gravitational pull on galactic dynamics. Despite its incredible distances, the Milky Way is our universe's neighbor in the larger universe. Expanding our horizon beyond our galaxy, we're looking not only at our own Milky Way, but also at our closest galactic neighbor, Andromeda, and a group of galaxies that includes 54 other smaller galaxies. This group is part of the Virgo supercluster, which itself is only a small component of the Laniakea supercluster, a massive structure spanning 500 million light-years and containing hundreds of thousands of galaxies. In a fascinating thought experiment that condenses the universe's 13.8 billion-year history into 1 year called the cosmic calendar, our perception of time is undergoing a dramatic change. In this calendar, each second represents approximately 437 years, allowing us to clearly visualize the vast history of space. January 1st. The Big Bang, the explosive birth of the universe, symbolically marks the cosmic saga leading up to the present moment, on the night of December 31st. As the cosmic year progresses, fundamental particles and atoms form in the earliest months, and the first stars burn in the dark space of the universe by the end of January. Galaxies start spinning in March, orbiting and gathering in the great cosmic dance that builds the universe. Our own Milky Way galaxy formed around May, setting the stage for the formation of the solar system. The formation of the solar system begins in August, when the Sun and its planets coalesce from a cloud of gas and dust. Earth is forming soon, but by September, it will have cooled enough for a stable crust to form and for the earliest forms of life. These early life forms are simple, microscopic organisms, but their existence is a momentous event in the cosmic calendar. Fast forward to December, and the pace of events accelerates. Complex life forms and begins to diversify in the oceans. By December 17th, the first land plants appear, followed by dinosaurs who dominate the landscape until they suddenly disappear around December 26th. This paves the way for the rise and diversification of mammals, leading to the first hominids stepping onto the scene in the final moments of December 31st. Human history, from the development of agriculture to the construction of the pyramids, from the Renaissance to the digital age, unfolds in the last few seconds of a space year. This humble view shows the speed of human existence in contrast to the vast, ancient expanse of the universe. The Big Bang Theory is a monumental explanation of the origin of our universe, which all began 13.8 billion years ago from a single, infinitely dense point. This primordial explosion continues the universe to this day. The evidence supporting this theory is deep and multifaceted, describing the earliest moments of the universe and its subsequent evolution. One of the strongest lines of evidence for the Big Bang comes from observations of the cosmic microwave background radiation. After this initial explosion, a faint cosmic hiss filled the entire universe. Discovered by accident in 1964 by Arno Penzias and Robert Wilson, the CMB is a uniform background of microwave radiation that is detectable in every direction we look. Its discovery provided a major boost to the Big Bang theory. As it was expected if the universe began in a hot, dense state, the uniformity of the CMB, with few variations or spins, also provides scientists with important information about the distribution of matter in the larger universe, forming galaxies and other large structures. Another pillar supporting the Big Bang theory is the observation that the universe is expanding. In the 1920s, Edwin Hubble established the theory that galaxies are moving away from us and that galaxies are moving faster. This observation can be compared to points on an inflated balloon that are spaced apart from each other, shows the expansion of the universe. A logical extrapolation from this observation is that if the universe is expanding now, it must have been smaller and denser in the past, eventually moving to a single point where it began to expand. The abundance of light elements in the universe, especially hydrogen, helium, and lithium, also supports the Big Bang theory. Predictions based on the theory suggest that in a hot, dense universe, the conditions were ripe for these light elements to form in the proportions observed today. The observed abundance of these elements in space closely matches the theoretical predictions of Big Bang nucleosynthesis, providing a strong empirical basis for the theory. This evidence, the cosmic microwave background radiation, observations of the universe's expansion, and the abundance of light elements make a consistent and compelling case for the Big Bang as the origin of our universe. A journey through the life cycle of a star, especially one similar to our Sun, reveals the story of cosmic change and evolution spanning billions of years. The story begins in the cold, dark incubators of dense regions filled with molecular clouds, gas, and dust. Pockets of gas within these clouds gradually accumulate under gravitational pull, eventually reaching densities and temperatures where nuclear fusion ignites in their cores. This flare marks the birth of a star, entering the main sequence phase of its life. In this main sequence, a star like the Sun fuses hydrogen into helium and releases a lot of energy. This process, which takes about 10 billion years for the Sun, is remarkably stable, balancing the inner gravitational box with the outer pressure of nuclear fusion. The light and heat from our Sun is about 4.6 billion years and will continue to provide for another 5 billion years, sustaining life on Earth and controlling the rhythms of the planetary system. The story takes a dramatic turn when the star runs out of hydrogen fuel. As the outer layers expand and cool, the core contracts and heats, turning the star into a red giant. At this stage, the star's diameter swells to several times its size. If it were to be with the Sun, it would encompass the inner planets, including Earth. In the heart of a red giant, helium is converted into fuel, combining with heavier elements such as carbon and oxygen. For stars of mass comparable to the Sun, this phase causes their outer layers to shed, creating a colorful cloud of gas known as the planetary mantle. The other is the central white quaternary, a dense Earth-sized remnant, but not as massive as the Sun. This white dwarf will slowly cool and disappear over trillions of years, ending the star's life cycle as a cool, dark, and dense object. As the Sun begins its inevitable journey to becoming a red giant, the changes will have profound effects on the planets of our solar system. This metamorphosis marked by a decrease in the Sun's size and surface temperature, will take place over billions of years. But its effects on the organisms of the planets orbiting the Sun will be varied and varied. The inner planets, including Mercury and Venus, suffer the most immediate and catastrophic consequences. As the Sun expands, it will completely envelop these planets, effectively condensing them due to intense heat and gravity. Earth's fate, though uncertain, hangs in a delicate balance. It can barely survive being swallowed, but will still experience extreme heat. This drastic increase in temperature could destroy the planet's atmosphere and evaporate the oceans, making it habitable and barren. Mars, a little ahead of the Sun, will undergo major changes. The increased sunlight will warm the surface of Mars, making it more suitable for holding an atmosphere and even liquid water on it. But this will be a temporary phase, as the Sun's continued evolution and eventual shedding of its outer layers will cause the Sun's luminosity to decrease and the distance to the rest of the planets to increase. The outer gas giants, Jupiter, Saturn, Uranus, and Neptune, will witness other changes. Increased solar radiation can alter their atmospheres, possibly pulling in lighter elements and changing their appearance and composition. Their moons, many of which are considered potential candidates for sustaining life, could see their ice-covered surfaces melt, leading to a temporary liquid water environment that could support life for a short time. As the Sun loses mass in its red giant phase, the gravitational pull on the planets will weaken, causing their orbits to widen and move farther apart. This shift could lead to major changes in the dynamics of the solar system, including orbital resonances, the potential ejection or destabilization of comets and asteroids in the Kuiper Belt and Oort cloud, sending them on new trajectories through the solar system. Eventually, as the Sun descends to White 4, the remaining planets will orbit a much darker, less massive star. The solar system will be in a completely different place, with the surviving planets receiving only a fraction of the light and heat they had before. This new, cooler solar system will be a silent testament to the Sun's once vibrant past. The death of a Sun-like star is not the end, but rather a fascinating transformation, one of the most beautiful phenomena known to astronomy, the eclipse of a planet. As the star sheds its nuclear fuel and sheds its outer layers, it creates a spectacular display of light and color, a celestial masterpiece that can illuminate space for thousands of years. This process, resulting from the evolution of a star beyond the red giant phase, represents the content of the stellar life cycle and the creation of new structures from the remnants of stellar death. As a Sun-like star enters the final stages of its life, it begins to lose its outer layers to space, driven by strong interstellar winds. What remains at the core is a hot, dense white dwarf that emits intense ultraviolet radiation. This radiation illuminates the emitted gas, shimmering in a kaleidoscope of colors. The complex shapes and patterns of the planet's crust, from rings, shells, and spiral structures to complex, irregular shapes, are the result of stellar winds, magnetic fields, and interstellar interactions. The misnomer planetary nucleus derives from their telescope observations of round planet-like disks, but they are actually large clouds of ionized gas orbiting the remnants of dying stars. Each planet's crust is unique, displaying different colors based on the gases present and the temperatures reached, just a few examples of the varied and fascinating shapes these crusts can take. Each is a testament to the complex processes at work deep inside the star. The formation of the planetary core is an important step in the processing of space material. Elements created in the center of stars and ejected into space form the basis of new stars, planets, and possibly life. In this way, The death of a star enriches the cosmic environment, contributing to the cycle of stellar birth and death that drives the evolution of the universe. Dark matter, the mysterious and invisible substance that plays an important role in the cosmic ballet that shapes the universe. Although it does not emit light and is not directly visible to telescopes, dark matter depends on its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Dark matter, which makes up about 27% of the mass-energy content of the universe, far outnumbers the ordinary matter that makes up stars, planets, and all life. The concept of dark matter arose from observations of galaxies and galaxy clusters that did not obey the laws of gravity as we understand them. In the 1930s, astronomer Fritz Zwicky observed that galaxies in clusters were moving so fast that they would have to break apart if visible matter held them together. Meanwhile, in the 1970s, Vera Rubin and Kent Ford observed that stars on the outskirts of galaxies orbited at speeds near the center, disproving the expectation that their speed would decrease with distance from the galactic center. These and other observations have shown that there is an invisible mass that exerts an additional gravitational force, leading to the dark gravity hypothesis. The gravitational pull of dark matter is crucial for understanding the formation and evolution of cosmic structures. Small changes in the density of matter in the early universe provided the seeds from which galaxies formed and grew. Dark matter, with its invisible scaffolding, amplified these initial disturbances, drawing simple gravity through the gravity box. This process led to the formation of stars, galaxies, and galaxy clusters, sculpting the web-like structure of the universe. Although the gravitational pull of dark matter helps shape the cosmos, its interaction with the expansion of the universe helps us understand the nature of the cosmos. After the Big Bang, the universe continued to expand, and over time, galaxies moved away from each other. The gravitational influence of dark matter works against this expansion, slowing it down. However, this acceleration is counteracted by dark energy, a mysterious force that causes the universe to expand at an accelerated rate. The interplay of dark matter and dark energy is a central topic in cosmology, as scientists try to understand how the universe can be simultaneously connected on a large scale, while simultaneously pulling itself apart. The discovery of dark energy emerged in the late 1990s from observations of distant supernovae. These observations showed that the universe is not only expanding, but that the rate of expansion is accelerating. This acceleration was unexpected. According to conventional wisdom, gravity was supposed to slow down the expansion. The force responsible for this acceleration, later called dark energy, is the fabric of the universe filled with a constant energy density that separates space. The exact nature of dark energy remains a mystery. One leading theory may be that this is a property of space, described by Albert Einstein's cosmological constant, a term he introduced in the equations of general relativity. According to this idea, empty space is not really empty, but has its own energy. As the universe expands, new space is created, and with it comes more energy, driving further expansion. Another hypothesis is that dark energy is a dynamic field, similar to electromagnetic fields, that varies with time and space. This concept leads to models in which the strength of dark energy can vary, affecting the rate of cosmic expansion at different times. However, no direct evidence for such a region has been found, leaving its existence in the realm of theoretical speculation. The fate of the universe, the subject of intense speculation and scientific research, depends on the battle between the forces of expansion and contraction. This cosmic battle, influenced by dark energy, dark matter, and the total mass and energy content of the universe, has several possible consequences for its ultimate fate. The question of whether the universe will expand forever and eventually collapse into itself is central to our understanding of cosmology and the nature of the cosmos. Current observations and theoretical models show that the universe is not only expanding, but also accelerating. This acceleration is due to a mysterious force known as dark energy that dominates the energy content of the universe. The repulsive force of dark energy works against the gravitational pull of matter, including the dark matter that binds galaxies together. Because dark energy drives the expansion of the universe, it leads scientists to believe that the universe will continue to expand indefinitely. The heat-death scenario of the universe, often considered in the context of its ultimate fate, is a concept based on principles. According to the second law of thermodynamics, the entropy of an isolated system will increase with time. On a cosmic scale, this translates to a future where the universe has reached maximum entropy, all energy is distributed equally, and there are no gradients left to drive processes that can convert energy into work. This state is often described as the final act of the universe, marking the cessation of all astronomical and physical activity in a cold, dark, and lifeless space. In this scenario, the universe will continue to expand, controlled by dark energy, spreading matter and energy more and more thinly. Over trillions of years, stars will burn off their nuclear fuel, galaxies will stop forming new stars, and existing celestial bodies will either collapse into black holes or disperse into the expanding universe. Black holes themselves slowly vaporize via Hawking rays, a quantum mechanical process that Stephen Hawking predicted would leave the universe with very few particles and radiation, spread evenly across an expanding space. The heat-death scenario leads to a universe where all entropy-increasing processes run their course, leaving a state of thermal equilibrium. At this equilibrium, the temperature throughout the universe will approach absolute zero, where energy exchange is impossible because everywhere is at the same temperature. The absence of temperature differences, hence the flow of energy, means that no work can be done, and the universe is static, unchanging, and unable to sustain any form of life or motion. The description of the end of the universe is based on our current understanding of physical laws and the observed acceleration of cosmic expansion. It suggests a slow, inexplicable slide toward a unified state rather than a dramatic conclusion. As dark as it may seem, the heat death of the universe is a future event that defies human understanding of time, spanning orders of magnitude longer than the current age of the universe. The Big Rip theory offers a dramatic and cataclysmic model for the end of the universe, different from the gradual cooling of the heat-death scenario. This theory is based on the behavior of dark energy, the mysterious force that drives the universe to accelerate. If the repulsive force of dark energy increases, it can eventually overcome the gravitational force that holds galaxies, stars, planets, and ultimately atoms together. The Big Rip theorizes an endgame where the fabric of the universe is torn apart, leading to a universe literally torn apart. The building of the Great Rip is based on a specific form of dark energy that grows infinitely in density. In such a universe, the rate of expansion is not only accelerating, but increasing. This scenario leads to a future where, at some point, the expansion becomes so fast and powerful that it begins to overcome all gravitational and electromagnetic binding forces. In the timeline leading up to the Big Rip, the galaxies will first drift apart as the space between them expands more rapidly. After this, the gravitational pull on individual galaxies will weaken, causing them to collapse. Solar systems, including our own, will continue to lose coherence, and planets will be thrown into the dark void as the bonds that bind them to their stars are broken. As the final moments approach, stars, planets, and even molecules will disintegrate, as the repulsive force of dark energy overcomes the forces that bind atoms together. In the latter case, the atoms would break apart, and the fabric of space-time would ceaselessly expand, leaving behind a universe without a single structure and a universe filled with individual particles drifting apart from each other. The Big Rip represents one of several speculative but theoretically plausible implications for the universe, depending on the precise nature of dark energy. If the power of dark energy grows over time, the Big Rip becomes a possible scenario. If dark energy remains constant or decreases, as in Einstein's cosmological constant model, the universe may follow a different path, such as eternal expansion or eventual collapse. The Big Bang is a theoretical scenario for the end of the universe, where, instead of expanding infinitely, space reverses its course and begins to contract, eventually collapsing in on itself. These exciting but terrifying concepts suggest that if the density of matter and energy in the universe is high enough to expand the control of dark energy, gravity will eventually win out, pulling everything into a single point of infinite density. In this scenario, the massive expansion of the universe witnessed after the Big Bang gradually slows down until the collective gravity of all cosmic matter and dark matter begins to stop the outward flight of galaxies. When this expansion stops, the contraction phase begins. This process would not have happened instantaneously, but would have mirrored the initial expansion of the universe over billions of years, but in reverse. As the compression accelerates, the galaxies begin to move closer together. This would be a drastic change from the current state of cosmic drift, which would lead to an increase in intergalactic interactions and collisions. These galactic mergers will be cataclysmic events, forming stars and dramatically changing the structure of galaxies. After galaxies merge, star systems begin to collide and merge, disrupting planetary orbits and causing stellar chaos. The night sky on other planets would look very different, filled with many denser stars, and conditions on this world would become increasingly hostile to any form of life. In the final stages of the Big Bang, when stars, planets, and eventually atoms collided together, the density and temperature of the universe would have risen dramatically. This phase may represent conditions similar to those in the early universe, but instead end in a singularity, where all the matter and energy of the universe is compressed into an infinitesimally small point, possibly setting the stage for another Big Bang, if the cyclic model, universe, LDS is correct. The concept of the multiverse introduces an interesting twist to discussions about the fate of our universe, suggesting that our universe may be one of many universes. Each universe within this potential multiverse may have its own laws of physics, initial conditions, and, consequently, a unique destiny. This idea not only expands the scope of cosmological speculation, but also suggests alternative possibilities that challenge our understanding of the cosmos. In multimedia, the fate of any universe, including our own, can be influenced by factors that are completely absent in other universes. For example, while our universe appears to be on a perpetual expansion path, leading to a heat death or Big Rip scenario, other universes may have different balances of matter, and dark energy, leading to fates such as the Big Winter, or even scripts outside of our stream. Scientific perspective. One interesting aspect of the multimedia theory is the idea of multiple universes, where each universe is like a bridge floating in high-dimensional space. These bubbles may periodically collapse or form through processes similar to cosmic inflation, suggesting that the birth and death of universes are events in a cosmic context. Within this framework, the fate of any universe can depend on interactions with other universes, or it may be determined by the specific circumstances of its inflationary history. The concept of multimedia also allows for physical constants and universes vastly different from our own. In some of these universes, the conditions may never allow for stars, galaxies, or life, while others may have completely different complexities and forms of life. This variability adds a great deal of complexity to the question of the fate of the universe, suggesting that the multiverse may have as many outcomes as there are universes. The strange and compelling laws of quantum mechanics, which govern the behavior of particles at the smallest scales, may also have profound implications for the ultimate fate of the universe. Quantum mechanics introduces uncertainty, superposition, and concepts that seem counterintuitive to classical intuition. Although these principles are primarily influential at the microscopic level, they can play an important role in understanding cosmic phenomena and the ultimate consequences of the universe. One area where quantum mechanics intersects with cosmology is in the realm of black holes. Stephen Hawking's quantum mechanical process. The Hawking radiation prediction suggests that black holes emit radiation and eventually evaporate over astronomical time. This evaporation process can have significant implications for the long-term evolution of the universe, especially in scenarios such as thermal death, where black holes become the main remnant structures. As they evaporate, the energy released may be one of the last significant events in the aging universe. Quantum mechanics can also influence the fate of the universe through the concept of quantum fluctuations. It is the temporal variation of the amount of energy at a point in space, as allowed by the Heisenberg uncertainty principle. In the early universe, quantum fluctuations are believed to have been the seeds for the formation of cosmic structures such as galaxies and large-scale structures. Moving this effect into the distant future, quantum fluctuations could lead to the formation of new vacuums or even new universes by mechanisms such as pseudo-vacuum breakdown, where a more stable vacuum state is achieved through quantum transitions. It can dramatically alter the fate of the universe, even creating new universes in multiple scenarios. Furthermore, the principles of quantum mechanics challenge our understanding of time and causality, central components in any discussion of the fate of the universe. Quantum entanglement, for example, suggests an instantaneous connection between particles, rejecting classical ideas of cause and effect. This may imply a more connected cosmic fabric, where the fate of the universe is not only a linear progression, but also includes non-local phenomena that can quickly understand or change its end. Quantum cosmology, which seeks to apply quantum mechanics to the entire universe, offers possibilities such as quantum creation, where quantum changes in existing space or the quantum vacuum can create new universes. This opens up discussions about cyclical or leapfrogging universes, where the death of one universe can lead to the birth of another, which can affect diversity theory and our understanding of our own universe's place in the wider cosmic context. The possibility of unexpected forces or phenomena that could profoundly affect the future of the universe remains a tantalizing and humbling prospect. Despite the incredible strides made in understanding the cosmos, from the laws of gravity that bind galaxies together to the quantum mechanics that govern subatomic particles, much about the universe remains mysterious and uncharted. The history of science is full of moments when the discovery of new forces or phenomena fundamentally changed our understanding, and the future of cosmological research suggests that similar discoveries may be possible. The dark sector, which contains dark matter and dark energy, represents a type of uncertainty that continues to defy scientists. These entities make up the vast majority of the mass energy content of the universe, but they interact with the observable universe in completely incomprehensible ways. Discovering new properties of these dark components, or an entirely new form of dark matter, could dramatically change our predictions about the fate of the universe. Moreover, The theoretical framework of physics itself suggests the possibility of undiscovered forces. For example, the search for a theory of everything, a unified framework that unifies quantum mechanics into general relativity, has led to proposals such as string theory and quantum gravity. These theories suggest the existence of additional dimensions and fundamental particles that may mediate forces or phenomena that are largely unaccounted for in our current models. Discoveries in this area could introduce new dynamics into cosmic evolution, opening up avenues for understanding the fate of the universe that we currently cannot understand. Another way that unknown forces can show up is through the study of cosmic anomalies, observations that don't fit well with existing models. For example, discrepancies in the observed velocities of galaxies within galaxy clusters and the outer stars in galaxies suggest that they originally contained dark matter. In the future, similar anomalies may be new forces or compositions of space. The conditions that prevailed during the beginning of the universe and the first fractions of a second after the Big Bang remain a mystery. Phenomena at these energy scales or at the earliest stages of cosmic inflation may leave traces that we have yet to properly interpret or even detect. These memories from the birth of the universe may hold the keys to understanding the forces or phenomena that shaped cosmic history and determined its ultimate course. The idea that humanity can play a role in shaping the fate of the universe combines the fields of cosmology and human ingenuity to invite speculation on a grand scale. Although the vastness of space and the forces that govern it are human endeavors, the rapid advancement of technology and our deepening understanding of the universe are forcing us to reconsider the impact that intelligent beings can have on cosmic scales. Humanity's ability to understand and manipulate the environment has changed the Earth, and our forays into space represent the first small steps toward influencing the wider cosmic landscape. Theoretical proposals such as the Dyson sphere, a hypothetical megastructure designed to harness stellar power, suggest that advanced civilizations may have directly harnessed stellar energy. Although currently beyond our technological capabilities, such concepts suggest that intelligent beings could significantly alter the local space environment. On a more speculative note, the pursuit of a unified theory of physics involves fundamental forces and the ability to manipulate particles that we cannot imagine. Advances in this field may one day allow the stabilization of star systems, the engineering of black holes, or the creation of artificial structures on a cosmic scale. The potential to prevent local astronomical catastrophes such as asteroid impacts, or to extend the lifespan of stars through advanced energy manipulation, could represent the first steps in the power to shape cosmic events. The concept of panspermia, where life is deliberately directed to other planets or star systems by an intelligent civilization, could see humanity become a vector of spread across the galaxy. In this way, the human factor can influence the development of other worlds, seed new evolutionary paths, or create conditions for the emergence of other intelligent species. The long-term survival and expansion of human civilization into space must overcome major challenges, including interstellar distances, the hostile environment of space, and the need to establish sustainable habitats beyond Earth. Achieving such breakthroughs requires not only technological prowess, but also cooperation and space resource management. Although humanity's influence on the fate of the universe may seem insignificant in the face of its vast scale and power, the potential for the development of our understanding and capabilities of the role of intelligent life in space cannot be underestimated. Whether through the direct manipulation of cosmic phenomena, the proliferation of life, or the pursuit of knowledge that alters our relationship with the universe, the human factor adds a dynamic element to the cosmic narrative. Today, we embark on an amazing journey through space and time. Imagine a galaxy billions of kilometers away from Earth, nestled between the Milky Way and Andromeda Galaxy. Imagine yourself surrounded by an infinite void, but bound by the invisible threads of time. But what is spacetime, and how does it shape the universe as we know it? Join us as we unravel the mysteries of this cosmic web, delve into the complex geometry of space, and explore its dynamic forces. From the emptiness of intergalactic space to the stunning beauty of distant galaxies, we will venture into the unknown and witness the wonders of the universe. So are you ready to embark on this fascinating odyssey? Don't forget to share your thoughts in the comments below. What secrets of space would you like to learn next? If you are as passionate about space as we are, click this subscribe button and join our community of space explorers. Imagine the universe as a calm, still network, like a quiet river flowing between the stars. But it is not entirely inactive. If we were to speed up time, we would see it change subtly and take everything away. Stars, clouds of gas, and even space-time in the form of invisible dark matter are all spinning toward them. For billions of years, our galaxy, the Milky Way, and its neighbor Andromeda have been moving closer together. Eventually, they will collide and merge into one large galaxy. But when that happens, most galaxies actually break apart. The universe stretches like a vast fabric. Galaxies ride these expansion waves, moving away from each other. As they do, their light stretches and reddens, a sign of an ever-accelerating universe fueled by mysterious dark energy. Around 8 billion years ago, the universe began in a cataclysmic event known as the Big Bang. In an instant, it expanded from an unimaginably tiny dot to astronomical proportions. But what caused this big explosion remains a mystery. From these primordial objects, matter clumped together to form filaments, clusters, galaxies, and stars. It is the story of small changes that create large cosmic structures. Our home, Earth, dances around one of these stars, the Sun. Not only is it here, there are planets, asteroids, and comets orbiting in space. The Sun's immense gravity creates a cosmic current that bends the fabric of spacetime and directs everything toward it. This is how the planets orbit. They don't fly into space, they're really making progress. But time around the Sun is pulled back like a cosmic magnet. Even the Moon and our moons are caught in this cosmic dance, orbited by Earth's gravitational pull. Away from massive objects like stars, it flows slowly at times and objects can easily escape its grasp. But as you get closer to a larger body like the Sun or Earth, space-time starts to compress and pull things along even faster. Therefore, rockets must reach incredible speeds to escape ground speed. This is why we experience waves on Earth. Just as the Moon's gravitational pull on our planet causes the oceans to rise and fall, the Earth's rotation affects spacetime, pulling it like a cosmic storm. When you throw an apple, even though it doesn't touch the ground, the rotation of the Earth affects it from a distance, changing its path. Deep inside the Earth, spacetime descends, trying to pull everything to the center. But Earth materials resist this pull and push back hard. So when we jump back down to the ground, it gives us a boost. At the core, where all power is united, if something can withstand incredible pressure, it would still be perfect. As you move toward the center, all the particles that make up spacetime move forward, bouncing off each other, until they eventually emerge on the other side of the Earth. If we somehow manage to jump off the planet, we're going in the opposite direction. In about 5 billion years, our Sun will reach the end of its life. It will not be able to sustain its pressure and will be pulled into spacetime. The core will disintegrate, creating a super-dense white quaternary, with the outer layers becoming a giant planetary core. But not all stars turn out that way. Somewhere far away there is a superstar 20 times the size of the Sun, and its end is near. Its core collapses and the outer layers explode in a spectacular supernova. Eventually, the core collapses into a small neutron star, placing two solar masses within 30 kilometers of each other. The gravitational pull of the cosmic web is so strong that even light is attracted, causing strange optical effects. Thousands of light-years away, a massive star is about to explode. Some black holes are born near other stars and orbit around them, asking for their stuff. This plasma creates a spinning disk, losing energy as it spirals toward the edge of the black hole. Closer to the center, the flow accelerates infinitely, tearing apart everything in its path. The network is so stretched that it separates the atoms and turns everything into spaghetti at the center. Our current theories cannot fully explain how space behaves at the quantum level in the universe. Nothing stops. When stars die, they mostly spin, collapsing at their cores to become black holes. Their rotation is like an ice skater pulled by their arms. This rotation is imprinted in spacetime, which continues to rotate. Below a certain distance within the black hole's ergosphere, the entire network is pulled into a faster-than-light vortex, pulling everything in its direction of rotation. Even light is deflected around a black hole below the horizon, where matter is falling faster than light. Such a black hole may have a second horizon, where its periodic rotation fights gravity and slows its fall. So there you have it. Black holes, space monsters, continue to amaze us with their mysteries. From their deepest depths to their amalgamation, they form the fabric of our universe. But the story does not end there. Thanks to groundbreaking discoveries like gravitational waves, we are looking deeper into space than ever before. How are you? You are part of this amazing journey. By sticking with our channel, you dive headfirst into the wonders of space science. Together we unravel the mysteries of black holes, explore the mysteries of the universe, and explore the limits of human knowledge. So if you are as passionate about space as we are, click the subscribe button. A central university is an education in this field. Development, artificial intelligence, business and analytics, paid internships and work at partner companies. Enter Central University, a university for future leaders of the IT and business world. 2,500,000 years ago, Andromeda Galaxy. Not far from the center of the galaxy, a giant star is dying. Its final seconds are followed by a tragic explosion. 1 trillion tons of red-hot plasma explodes in a huge cloud, turning nearby planets and moons to dust. A powerful electromagnetic pulse pierces space in all directions. Millions of years later, it will reach Earth. 1885. Earth. The attention of all astronomers on the planet is focused on this amazing astronomical event. The brightest flash in the Andromeda Nebula briefly highlights the nearest lights with its brightness. This amazing supernova is named S Andromeda, and its anomalous parameters have long puzzled astronomers. But after 6 months, the star quickly dimmed. It soon disappears from heaven forever. Unfortunately, at the time of the flash, generally accepted ideas about the structure of the universe were far from modern. In those days, astronomers couldn't measure the distance to celestial bodies, so the bright spot in the constellation Andromeda, also known as Object M31, reflected a simple nebula at the edge of the Milky Way. At the same time, the emergence of new, more powerful telescopes and the development of space technology gradually changed the situation. In the 1920s, observations by Edwin Hubble and other astronomers proved that the Andromeda Nebula is another galaxy like the Milky Way. About a century has passed since then, and science has advanced a lot in that time. The Andromeda Galaxy is known to have a spiral structure and contain approximately 1 trillion stars. However, it is more than 150,000 light-years in diameter and has a relatively small mass, ranging from 800 billion to 1.5 trillion solar masses, about the same as the Milky Way. This is thought to be due to the abundance of red dwarfs and the dark matter in their composition. Like all spiral galaxies, Andromeda has a massive core at its center, made up of millions of densely packed stars. Its light is so bright that it overwhelms observational instruments, making it impossible to distinguish individual lights. For this reason, the remnants of the 1885 supernova, known as S Andromeda, were not discovered for a long time, even though the surviving records clearly indicate that it exploded near the galactic center. Only in 1988, 103 years after the legendary outburst, A small mound was discovered a short distance from the center, a dark spot that stood out against the background of the dark center. Through spectral analysis and modeling of its motion, it was possible to reliably confirm its presence as an Andromeda remnant. This cosmic object was the first supernova discovered outside the Milky Way. Looking closely at Andromeda's core, it's easy to see how it's uniquely different from other spiral galaxies. This is an unusual binary core, the origin of which is still not fully understood. The brighter and wider part is a giant supercluster of many bright stars located slightly away from the geometric center of the galaxy and about 7 light-years in size. The second part, however, closer to the center, is noticeably darker and smaller. Its diameter is about 1.3 light-years. This region is believed to be hidden inside a supermassive black hole 50 million times more massive than the Sun. The nature of such a strange phenomenon remains a topic of scientific debate. According to some speculations, in the distant past, M31 absorbed and dispersed a very large companion galaxy. The bright area is the remnant of its core. Other hypotheses suggest that Andromeda's core still has a single structure. However, it separates with opaque dust, creating an unusual optical effect. Because of the galaxy's remoteness and inhospitality in space, it is impossible to collect enough data to confirm one or the other hypothesis. Meanwhile, by continuing to walk through the central region of Andromeda, you can see one of the most mysterious objects in this galaxy. You can read its complicated name on your screens. The main feature of this celestial body is that it is almost impossible to see even with the most powerful optical telescope. However, when you use X-rays, everything changes. In this part of the spectrum, this light is the brightest point in the galaxy. Observations show that the object is a system of 2 components, one of which is a low-mass neutron star. Its radius is only a few tens of kilometers, and a complete revolution around its axis takes 3 seconds. The second luminary in the system, larger but relatively dim, is probably a red giant. Calculations show that the total mass of the 2 components does not exceed 3 solar masses, and the distance between them is very small. Every 4 hours, a neutron star is captured by its star, so its radiation power drops sharply, then returns to its previous values. Also, due to the small distance between the luminaries, the neutron star gradually absorbs its companion, thus constantly increasing its mass. According to calculations, this process will last tens of millions of years. Eventually, the second light will be disrupted by the tidal force and become a bright and hot ring dome. At the same time, this spectacular object is one of the many lights that tightly surround the center of Andromeda. Together, they form a large scale about 12,000 light-years in diameter, which has a remarkably elongated shape. There is also the announced M31, but it is narrowly oriented to us and is almost invisible from Earth. It is estimated to be about 17,000 light-years long and about 6,500 light-years wide. Overall, the central part of the Andromeda Galaxy makes up about 30% of its mass. As we get farther and farther away, we see that the edge serves as the base for 2 giant spiral arms, the majestic coils that encompass the galactic center. At the same time, there are dark gaps between them, the width of which is greater than the Milky Way, and it reaches 13,000 light-years. Calculations show that Andromeda's arms contain 56% of the galaxy's stellar mass, as well as some dark matter. Under the influence of gravity, dust and gas are concentrated in the arms of stars, forming star formation regions. Over time, these gas-dust clouds form into scattered clusters and associations that contain young stars. Their light is reflected and scattered by the cosmic cloud, allowing the galactic disk to glow with fantastic color. One of these clusters is home to a super-bright star called AE Andromeda. It is one of the brightest stars in the galaxy and is a hot blue giant whose luminosity varies with no visible signs. Such things are called clear blue changes and are very rare. Currently, only a few dozen of these lights are known. Due to the high temperature and pressure, the outer layers of A and Andromeda are always in a state of unstable equilibrium. Processes in a star's interior are largely chaotic and unpredictable. From time to time, the red-hot plasma streams collide with each other, creating the brightest lights, changing the brightness of the object by tens of times. Hypothetically, the most powerful of them could increase the brightness of the star by several million times. Such a phenomenon is called a pseudo-supernova and can happen at any moment. Measuring the parameters of such an unstable star, combined with its great distance, is a very difficult task. Nevertheless, modern ultra-precision telescopes have determined that Andromeda's mass is within 50 to 120 solar masses, and that the peak radius of the pulsation is about 55 times the radius of our star, which is only slightly less than the orbit of Mercury. In this case, its surface temperature is about 20,000 Kelvin, and its brightness is 700,000 times higher than the Sun. Like all blue giants, A Andromeda produces the strongest stellar wind, estimated to reach speeds of up to 100 kilometers per second. Therefore, the object loses about 2 quadrillion tons of matter per second. This means that its mass is decreasing every year by an amount similar to that of 10 Earth-like planets. However, for such a big star, it's almost imperceptible. In fact, AI Andromeda completes its evolution faster by losing at least 1/10 of its mass from the stellar wind. The fact is that even though 2 million years is small by cosmic standards, AI Andromeda has passed most of its life cycle. It is estimated that within the next million years the luminary will explode in a supernova, leaving behind a black hole surrounded by a giant cloud of gas and dust. When we talk about the age of stars, we do not take into account that they are not evenly distributed throughout the galaxy. So we can look into Andromeda's past and see how it came to be. The oldest stars, about 13 billion years old, are concentrated in the central part of the galaxy. In contrast, the disk and spiral arms contain mostly young light bodies that formed 4 billion years ago. Many young stars born several million years ago are also located here in multi-star cradles. Hence, in the early stages of its evolution, M31 was smaller in size and more elliptical in shape. By analyzing the parameters of individual Andromeda lights, we can define such an important but at the same time common concept as the habitable zone of the galaxy. The concentration of stars in Andromeda's core, as well as the high radiation and unstable orbits of potential exoplanets, are thought to make this zone inhospitable for the origin of life. Meanwhile, distant planetary systems located on the fringes of the galaxy are poor in heavy elements, resulting in a lack of Earth-like rocky planets. Therefore, only the intervening region of the galaxy can be considered hypothetically habitable. In such a zone, a few tens of thousands of light-years from the center of the galaxy, there is a small dark object called Mega ML7. It represents a red giant whose mass is relatively small and is about 50% of the mass of the Sun. In 1999, thanks to a lucky coincidence, astronomers were able to record the phenomenon of microlensing, during which they were able to study in detail such a unique and distant cosmic body. The measurement was able to determine the mass and spectrum of the light, as well as its surface temperature, about 3,700 Kelvin. But the most important observation is the rhythmic deviation of the star's trajectory from its main direction of motion. Such changes suggest that the luminary may have a fairly massive companion. The object in question is called Mega ML7b and is now considered a potential exoplanet. If confirmed, it would be the first astronomical exoplanet discovered outside the Milky Way. Little is known about this object, but calculations suggest that it is most likely a gas giant with a mass of about 3 Jupiterian. There is information that the diversity of chemical elements, this system is probably not inferior to ours. So the possibility of meeting within the most diverse types of planets is high. Not only gas giants, but also rocky celestial bodies that resemble Earth. Another feature catches the eye when observing the Andromeda Galaxy. These are multi-star clusters and associations, far more numerous than the Milky Way. In total, about 460 globular star clusters and about 10,000 are known in M31, as well as several dozen large star associations. Some of them are concentrated in the center of the galaxy, others are scattered in the halo, and others are located in its spiral arms. One of the largest and most prominent structures is the NGC 206 cluster located at the edge of the galactic disk. Previously, this association was considered a globular cluster, but now, due to its size, it has received a higher status and is called a star association. This region of outer space, with a radius of 200 light-years, contains about 300 bright stars and countless others, with a total mass of about 200,000 suns. Their combined luminosity is so great that the association is visible from Earth in a telescope with the center and arms of the galaxy. According to observations, NGC 206 formed as a result of the merger of at least two large gas-dust clouds separated by a dark band of interstellar dust. One of them is about 10 million years old, and the other is significantly older and formed about 50 million years ago. One giant bulge became a point of attraction for interstellar gas, creating a vast area of star formation. Over time, some of its light will radiate into the surrounding space. The rest form a large globular cluster. M31's disk galaxy has many such formations, and not all of them were originally formed within him. Many large star clusters are believed to be remnants of past great cosmic catastrophes. Andromeda is estimated to have absorbed more than 100 satellite galaxies in total. Some of them disintegrated without a trace. Others turned into a giant star stream. A collision with an object called M32 can be considered the largest. This compact elliptical galaxy is located 17,000 light-years above the disk of Andromeda. Its diameter is about 8,000 light-years, and for such a small size, this galaxy has a fairly high mass, about 1 billion suns. At the center of M32 is a supermassive black hole, 2.5 million times more massive than our star, which is amazing for such a compact object. In fact, M32 is the remnant of a larger galaxy that survived the Great Catastrophe. Data from the Spitzer orbiting telescope show that about 800 million years ago, a large satellite galaxy smashed into Andromeda's disk at high speed, leaving an impressive hole in one of the spiral arms. M32 lost most of its stars in the collision and is unlikely to return to its former appearance. It may be a complete elliptical galaxy or a small spiral galaxy with only the central portion remaining. In addition to M32, Andromeda has about 30 satellite galaxies bound to it by invisible gravitational strings. The brightest and largest of these is M110, which is about 15,000 light-years in diameter. Most of the rest are spherical galaxies and are located 1 million light-years away. Nevertheless, together they form the Andromeda subgroup, which belongs to the local group. Its other members are the Milky Way and its surroundings, as well as the galactic triangle and other objects. The constant force of gravity gradually pulls the local group together, causing the Andromeda Galaxy to move toward us at a speed of more than 300 kilometers per second. In a few billion years, Andromeda will merge with the Milky Way to form a large elliptical galaxy. The grandiose gravity will shift the lights of the two wanderers, scattering them unexpectedly through space. At this point, our planet will be burned mercilessly by the destructive rays of the dying sun, or completely disappear in the ocean of glowing plasma. It is almost impossible to predict what will happen to humanity. Will we populate other worlds unrecognizably altered by natural conditions? Or will we be lost without a trace? As with ancient species, this question is difficult to answer with certainty.
In the search for extraterrestrial life, scientists use a variety of methods that combine advanced technology and eternal curiosity. One major approach is to study exoplanets, planets orbiting stars beyond our Sun. Using instruments such as the Kepler Space Telescope, and its successor, the Transiting Exoplanet Survey Satellite, TCS, scientists identify potential exoplanets by observing the waning of a star's light as a planet passes in front of it. Once exoplanets are discovered, they are analyzed for their suitability for life. These include calculating a planet's distance from the star to determine if it is in a habitable zone where conditions may be suitable for the existence of liquid water, a key ingredient for life as we know it. In addition, powerful observatories, such as the soon-to-be-launched James Webb Space Telescope, will probe the atmospheres of these distant worlds in search of biosignatures, chemical markers such as oxygen, methane, or water vapor that may indicate the presence of life. Another intriguing method involves studying extremophiles here on Earth. Extremophiles are organisms that thrive in extreme environments, such as the intense heat of hydrothermal vents at the bottom of the ocean, the acidic environment of sulfuric hot springs, and the cold radiation regions of Antarctica. Understanding how life can survive in such harsh conditions allows scientists to understand how possible it is for life to exist in similar conditions in other parts of the solar system and beyond. In our solar system, missions such as the Mars rovers, including the latest Mars rover Perseverance, are equipped with sophisticated instruments designed to detect signs of past or present life on the red planet. Similarly, missions to icy satellites such as Europa, which have oceans beneath the surface of their icy crust, are searching for biological evidence of life. In addition, radio telescopes participating in the Search for Extraterrestrial Intelligence (SETI) program are listening for signals from advanced extraterrestrials. Each method, whether observing distant exoplanets or exploring nearby moons and planets, represents a step forward in humanity's quest to answer one of our deepest questions. Are we alone in this world? Studying the most important thing on Earth has enriched and expanded the search for life on other planets. Extremophiles are organisms that thrive in conditions previously considered uninhabitable. Extremely high or low temperatures, high pressure, high acidity or alkalinity, and high levels of radiation. These amazing adaptations challenge the traditional parameters of life-supporting environments and indicate that life can exist in a much wider range of conditions than previously thought. For example, the discovery of thermophiles, which thrive in the boiling waters of hydrothermal vents deep in the ocean, has led scientists to ponder the possibility of life on celestial bodies with similar environments. Take, for example, the icy moons of Jupiter and Saturn, Europa, and Enceladus, which are thought to have subsurface oceans kept warm by gravitational interaction with their parent planets, creating conditions similar to these deep-sea vents. Similarly, acidophiles and alkalophiles, the search for life in the sulfuric acid clouds of Venus or alkaline hydrothermal vents on Mars, has been inspired by extremophiles that live in highly acidic or basic environments. Moreover, the study of extremophiles, such as radio-resistant microbes that can survive extreme levels of radiation, is expanding potential habitability zones in our solar system and beyond. Mars, with its thin atmosphere and high levels of radiation on the surface, could be home to microbial life underground, where it can be protected from the harshest conditions. Analogues, such as the dry valleys of Antarctica, where psychrophiles, cold-loving organisms, thrive, also serve as Earth's model for potential life forms that could exist on the frozen plains of moons such as Europa or Enceladus, or even in the polar regions of Mars. Extremophiles demonstrate the incredible resilience of life and have encouraged scientists to think more broadly and creatively about where life can exist. The discovery that life can thrive in Earth's most extreme environments expands the range of conditions considered suitable for life and encourages astrobiologists to look for signs of life in places previously thought improbable. This groundbreaking perspective underscores our growing understanding of the universality of life and fuels optimism that we may one day find life beyond Earth. One of the strongest pieces of evidence for the possible existence of extraterrestrial life is the discovery of exoplanets in the habitable zone of their star, or the Goldilocks zone, where conditions may be optimal for liquid water to exist on the planet's surface. Since the launch of the Kepler Space Telescope, scientists have identified thousands of exoplanets, and several of them are in this habitable zone. These planets, such as Kepler 452b and Proxima Centauri b, offer intriguing possibilities due to their Earth-like conditions that could theoretically support life. The discovery of organic molecules in space adds another layer to the evidence. Organic molecules, such as amino acids, are the building blocks of life, and their presence in meteorites, comets, and the interstellar medium suggests that the ingredients for life may be widespread throughout the galaxy. In particular, the detection of complex organic compounds on Saturn's moon Titan and in plumes of water vapor ejected from the ocean beneath Enceladus's icy crust hint at chemical processes that could potentially support life. Closer to home, Mars provides tantalizing hints of the existence of life in the past and possibly in the present. The Mars rover Curiosity has detected bursts of methane in the Martian atmosphere, which on Earth is mostly produced by biological activity. While methane can also be produced by geological processes, its seasonal fluctuations on Mars lead scientists to speculate that microbial life may be producing it. In addition, ancient riverbeds and lake deposits have been found in sedimentary rocks analyzed by the Mars rovers, suggesting that liquid water, a crucial ingredient for life, once flowed on the surface of Mars for a long time. Another compelling piece of evidence comes from the study of extremophiles on Earth, organisms that can survive in the most inhospitable environments. These include microbes found in the acidic hot springs of Yellowstone, the icy ice of Antarctica, and the crushing depths of the Mariana Trench. The existence of such resilient life forms expands our understanding of the possible diversity of life and indicates that life can potentially survive the extreme conditions found on other planets and moons. Taken together, all of this evidence has generated a great deal of enthusiasm and has prompted continued research in the search for extraterrestrial life. While none of this evidence supports the existence of life beyond Earth, each discovery suggests that life as we know it, or do not yet know it, may well exist somewhere else in the cosmos. The evolution of life in environments very different from Earth's challenges our imagination and scientific understanding, but the principles of biology and evolution allow us to hypothesize how such life forms might have evolved. For example, on a planet with high gravity, evolutionary pressure may produce organisms with strong, robust structures that can withstand increased force. These creatures may have much denser muscles, more powerful limbs, and a compact, squat physique to support their body structure. Increased gravity is also likely to affect the development of a cardiovascular system designed to effectively combat the force pulling blood downward. In environments with high levels of radiation, such as a planet orbiting a star that emits intense ultraviolet or X-ray radiation, life forms can evolve unusual mechanisms for DNA repair and resistance to radiation. For example, microbial equivalents of life could possess highly efficient enzyme systems that rapidly repair damaged genetic material, and multicellular organisms could develop protective layers of pigment or exoskeletons to protect their internal organs. Such adaptations could mirror some extremophiles on Earth, such as the radio-resistant bacterium Deinococcus radiodurans, which can survive incredibly high doses of radiation due to its impressive DNA repair capabilities. In chemical environments very different from Earth's, such as Titan's methane lakes, life may evolve using very different biochemical processes. Instead of water, These organisms may use liquid methane or ethane as a solvent for their biological processes, leading to biochemical processes radically different from our carbon-based life. Their cellular structures may consist of membranes that can withstand extreme cold, and their metabolic processes must be highly efficient to generate energy under such conditions. Scientists hypothesize that the basis for such biochemistry may be silicon rather than carbon, providing a theoretical basis for silicon-based life that could function in these exotic environments. Photosynthesis, a fundamental process for many forms of life on Earth, can also undergo radical changes under different types of stars. On a planet illuminated by a dim red dwarf star, photosynthetic organisms may develop pigments that can absorb the infrared light that is abundant from such stars. Conversely, on planets orbiting hotter stars that emit more ultraviolet light, organisms may develop defense mechanisms and pigments that effectively capture and utilize this more energetic light, protecting themselves from its damaging effects. These hypothetical scenarios demonstrate the incredible adaptability of life governed by the principles of evolution by natural selection. Although the exact forms and functions of extraterrestrial life remain speculative, studying extremophiles on Earth gives us invaluable insights into how life can thrive in environments vastly different from our own. This will expand your understanding of the diversity and adaptation of the universe and help us explore and search for life beyond our world. The discovery of microbial life on Mars will be a major scientific breakthrough with far-reaching consequences, changing our understanding of the universe and our place in it. First, this clearly shows that life is not unique to the universe and suggests that the conditions necessary for life are greater than we think. This greatly increases the chances of finding life elsewhere in space, especially on the many planets found in the habitable zones of their star systems. One of the major scientific implications will be the study of the geology and climate history of Mars. Microbial life has probably adapted to Mars's current conditions, but understanding its origins could reveal vital information about Mars's past environment. If life originated independently on Mars, this suggests that it could arise in a wider range of conditions than those on early Earth. In addition, if Martian microbes share similarities with terrestrial life, it could support the theory of panspermia, which suggests that life can spread to planets via meteorites, comets, or other celestial bodies. This discovery could spur significant advances in astrobiology, especially in developing methods and technologies to detect life in extreme environments. Such findings could spur missions to other celestial bodies in our solar system, such as Europa, Enceladus, and Titan, which are also considered potential habitats for life. It could also accelerate funding and research for more sophisticated space missions designed to study these distant moons and planets with the precision needed to detect microbial communities. Ethically and philosophically, the discovery of Martian microbes will challenge humanity's self-perception. It will lead us to think about the uniqueness of human life and the broader potential for intelligent civilizations in the universe. The discovery could also influence debates about the moral aspects of colonizing Mars or other celestial bodies. Protecting Earth's ecosystems will become a priority, changing the legal and ethical framework for space exploration. From a practical standpoint, this discovery has important implications for planetary defense protocols. Current measures are designed to prevent contamination of Earth and other atmospheric bodies. If life is found on Mars, it will be more important to ensure that terrestrial microbes do not harm the ecosystems of Malaysia, and so on. It could lead to better methods of analyzing spacecraft and better methods of isolating samples returned to Earth. The discovery of microbial life on Mars would be a watershed moment in science, influencing our understanding of biology, stimulating technological and research advances, and prompting deep ethical and philosophical reflection. It would mark a transformative step in humanity's quest to comprehend the full scope and diversity of life in the universe. SETI researchers searching for extraterrestrial intelligence use a range of sophisticated methods and technologies to look for signals from intelligent civilizations beyond Earth. At the heart of their efforts are powerful radio telescopes that scan the sky looking for radio waves that may indicate artificial rather than natural origins. Telescopes are capable of detecting a wide range of frequencies, but SETI scientists often focus on a narrow band around 1,420 MHz, known as the water hole. This frequency is important because it is naturally emitted by neutral hydrogen, the most abundant element in the universe, and may be a logical choice for an intelligent civilization attempting interstellar communication. The search involves not just random listening, but an organized approach to data collection and analysis. Advanced algorithms and software are used to sift through vast amounts of collected data, screening out Earth origin noise and other celestial sources of radio waves. The goal is to identify narrow-band signals that stand out from the random hiss of the cosmic background, as such signals are thought to be produced by technological sources. Projects like SETI at home have even enlisted the help of millions of volunteers around the world who use the computing power of their personal computers to analyze snippets of data, democratizing the search and exponentially increasing the computing power available to researchers. Optical SETI is another promising field, involving the use of optical telescopes to search for short but powerful laser pulses that could be sent by distant civilizations. These pulses, detectable over vast interstellar distances, would be a clear indicator of intelligent technology. Modern photodetectors mounted on telescopes scan the sky, looking for such fleeting bursts of light that are distinct from the continuous glow of stars. Another layer of complexity is added by targeted searches that focus on specific star systems recognized as potentially habitable exoplanets. Thanks to missions such as Kepler and TESS, our understanding of exoplanets has improved, and SETI researchers can now point their instruments at the most promising candidates, increasing the likelihood of finding something noteworthy. In addition, SETI research is not conducted in isolation, but in collaboration with other astronomical observatories around the world. This coordination improves their ability to quickly verify signals that can eliminate terrestrial interference, so that each candidate signal is scrutinized from multiple perspectives. The detection by a known planet of a signal from extraterrestrial life will have far-reaching implications that will change our understanding of man's place in the cosmos. SETI researchers carefully document their findings and engage in peer review processes to verify possible conclusions. Until that fateful day arrives, the work done reflects the human desire to answer one of our deepest questions. Are we alone in this world? The WOW sign, discovered in 1977, is one of the most exciting and sustained in the search for extraterrestrial intelligence. On August 15th of that year, Jerry R. Ammon, an astronomer working at Ohio State University's Big Ear Radio Telescope, observed an unusual radio signal that was 22 times stronger than Earth's background. The sign, which lasted 72 seconds and was so impressive, was recorded by Etchem on a computer monitor with WOW written on the side, giving the sign its now familiar name. One of the mysteries surrounding the WOW symbol is its origin. The signal was found to originate somewhere in the constellation of Sagittarius, near the star group Chi Sagittarius, about 120 light-years away. However, despite many subsequent attempts to detect the signal, Ammon and subsequent astronomers were unable to reproduce or identify it. This scandal led to widespread speculation that the WOW brand was either a foreign proposition or a product of its rarity and uselessness. The characteristics of the symbol can cause violence. Mark WOW. It has a narrow bandwidth, only about 10 kHz, indicating an artificial origin. Cosmic sources typically emit a wide range of frequencies, making such narrow band signals highly unusual and consistent with the kind of focused transmissions we might expect from an intelligent civilization attempting to communicate across vast interstellar distances. Moreover, its frequency, approximately 1420 MHz, coincides with the emission line of neutral hydrogen, a universal marker that scientists believe is ideal for interstellar communication. Several hypotheses have been proposed to explain the WOW signal, ranging from interstellar scintillation to earthly interference. However, none of these have been conclusively proven. The possibility that it could have been a deliberate transmission from an alien civilization continues to excite the imagination, although the lack of repeat detections makes it difficult to form firm conclusions. Some skeptics speculate that the signal could have been an Earth transmission reflected off a piece of space debris, but this remains just a guess with no concrete evidence. Adding to the mystery is the fact that the Big Ear telescope was designed to survey the sky in two orthogonal directions, but the signal was only detected in one channel and not the other. If the signal was of terrestrial or near-Earth origin, it would likely have been detected in both directions. The duration and shape of the signal also do not match known satellite transmissions, further complicating attempts to explain it with conventional sources. The elusiveness of the WOW signal underscores the difficulties inherent in the search for extraterrestrial intelligence. It serves as a reminder of both the vastness of space and the limitations of our detection capabilities. Decades later, the mystery of the WOW signal continues to inspire professional astronomers and amateur sky watchers alike, in the hope that perhaps one day a similar signal could provide more compelling evidence for the existence of intelligent life beyond Earth. In the meantime, WOW. The signal remains one of the most compelling mysteries in the annals of astronomy. The potential existence of life on the moons of Jupiter and Saturn has become a central theme of astrobiological research, primarily because of the unique environments these distant worlds offer. Europa, one of Jupiter's moons, and Enceladus, orbiting Saturn, are particularly attractive because of their subsurface oceans, which are kept liquid by tidal heating resulting from gravitational interactions with their parent planets and neighboring moons. A vast ocean is believed to lie beneath the frozen crust of Europa, whose smooth, icy surface is crisscrossed by dark bands and ridges. The proof is in the observations of the Galileo spacecraft, which has detected a magnetic field indicating the presence of a salty conductive liquid beneath the ice. This subsurface ocean may be in contact with the rocky mantle, potentially allowing the chemical interactions necessary to support microbial life. If hydrothermal vents like those found in Earth's oceans exist on Europa's seafloor, they could provide the energy and nutrients necessary for life. On Earth, these deep-sea vents are home to teeming ecosystems teeming with life, independent of sunlight and relying on chemosynthesis to convert chemicals into energy. Enceladus, though smaller in size, presents an equally interesting case. The Cassini spacecraft made remarkable discoveries during flybys, capturing geysers erupting from the Moon's south polar region. These plumes are composed of water vapor, molecular hydrogen, and organic compounds, suggesting the presence of a subsurface ocean beneath the ice shell. The presence of molecular hydrogen found during the Cassini survey indicates hydrothermal activity on the ocean floor, where the interaction of water and rocks produces hydrogen. Such environments may provide a source of chemical energy for life, similar to ecosystems found near Earth's hydrothermal vents. Titan, another moon of Saturn, offers a different but intriguing environment for potential life. Unlike Europa and Enceladus, Titan has a dense nitrogen-rich atmosphere and liquid hydrocarbon lakes on its surface, consisting mostly of methane and ethane. While this is very different from the water-based life we know, it's conceivable that life could have evolved using these hydrocarbons as solvents. Scientists speculate that Titan's exotic chemistry may contribute to the formation of complex organic molecules, and possibly prebiotic chemistry that could serve as a precursor to life. Ganymede and Callisto, two of Jupiter's other major moons, also have features that indicate the presence of subsurface oceans. Although it is less studied, the possibility of liquid water beneath thick layers of ice adds it to the list of intriguing candidates. The idea that life can survive in these alien environments is supported by the discovery on Earth of Extremophiles, organisms that thrive in extreme environments, from boiling acid springs to deep underground rock formations, demonstrating the amazing adaptability of life. Exploring these moons to confirm the existence of life involves several technological challenges and future missions. Instruments designed to analyze the composition of surface ice, study plumes, and potentially drill through layers of ice to reach the deep oceans are in various stages of development. NASA's upcoming Europa Clipper mission is designed to conduct a detailed exploration of Europa's icy envelope and subsurface ocean, while the European Space Agency's JUICE mission will study Jupiter's icy moons, including Ganymede. Overall, the moons of Jupiter and Saturn represent some of the most promising places in our solar system to search for extraterrestrial life. The presence of subsurface oceans, organic molecules, and energy sources on these distant worlds creates compelling conditions in which living organisms can exist. The discovery of such life will revolutionize our understanding of the biology, biochemistry, and potential prevalence of life in the universe, with profound implications for our place in space. Confirming the existence of extraterrestrial life is a formidable scientific challenge with many technological, methodological, and philosophical problems. One of the main challenges is the vast distances and scale of space. Even in our solar system, places like Mars, Europa, and Enceladus require a significant investment of time and resources. Interstellar distances exacerbate this problem. The nearest star system, Alpha Centauri, is more than 4 light-years away, making it impossible to directly explore with current technology. Another major obstacle is the search for and identification of indirect markers of life, or biological signatures. They take many forms: chemical compounds, various atmospheric compounds, and even complex organic molecules. For example, the presence of methane bursts on Mars, detected by the Curiosity rover, remains intriguing but inconclusive because such methane may be produced by geologic rather than biological processes. Similarly, observing oxygen, methane, or water vapor in the atmospheres of exoplanets with telescopes like the forthcoming James Webb Space Telescope may hint at life, but distinguishing biological sources from abiotic sources is very difficult. The environment itself presents serious obstacles. Harsh conditions such as extreme radiation, low temperatures, or high pressure require specialized equipment to explore and collect samples. Mars rovers and landers designed to explore such environments must be robust and capable of performing complex analyses remotely with minimal error. Technological limitations also extend to our current inability to drill deep through ice shelves to access subsurface oceans on moons such as Europa and Enceladus, where life could potentially exist. Pollution control is another critical issue. Ensuring that potential life found on other planets or moons is truly extraterrestrial and not a stowaway from Earth requires careful sterilization of spacecraft and instruments. Conversely, returning extraterrestrial samples to Earth must be done with extreme care to avoid contaminating our biosphere with potentially unknown and dangerous microorganisms. Scientific consensus and reproducibility further complicate the confirmation process. Any claims of the discovery of extraterrestrial life should be subject to scrutiny, peer review, and independent verification. The implications of such a discovery are so great that the scientific community has exceptionally high demands for evidence. This means that even if a potential biosignature is detected, it must be observed consistently and confirmed by multiple lines of evidence and by different teams of researchers. The detection of intelligent extraterrestrial life presents a number of challenges. Projects such as SETI involve listening for radio signals from intelligent civilizations, but deciphering these signals, distinguishing them from anthropogenic interference, and confirming their extraterrestrial origin is a complex and difficult task. The famous WOW, discovered in 1977, this is a good example of an exciting but unreproducible discovery that led to debate and further research without definitive conclusions. Finally, there are philosophical and definitional problems. What is life? Traditional definitions based on terrestrial biology may not be applicable to organisms with different biochemical compositions. The concept of life we don't yet know is forcing scientists to expand their criteria and methods to ignore other life forms because they don't fit past assumptions. Confirming extraterrestrial life requires traveling vast distances, developing advanced technologies, managing the risks of contamination, ensuring reproducibility and reliability of scientific data, deciphering potential intelligent signals, and expanding our ideas of what life might be like. These challenges are daunting, but also stimulate innovative solutions and interdisciplinary collaboration, pushing the boundaries of science and our understanding of the universe. The discovery of extraterrestrial life will revolutionize our understanding of life on Earth, affecting fields as diverse as biology, philosophy, astronomy, and even theology. From a biology perspective, the detection of extraterrestrial life would provide invaluable insights into the diversity and adaptability of life. This would expand our understanding of biochemistry beyond the Earth concept and provide a comparative basis for studying the principles of life. For example, if extraterrestrial life is discovered to use a biochemistry different from carbon-based life, perhaps silicon-based or based on a completely unpredictable molecule, this would force a rethinking of the fundamental assumptions for life and could reveal new biochemical processes previously thought impossible. This discovery will breathe new life into evolutionary biology, opening a new context for studying the evolution of life in different environmental conditions. On Earth, evolution is influenced by various factors such as climate, geography, and the presence of chemicals. The discovery of life that evolved in other environments, such as the high radiation environments of an exoplanet orbiting a red dwarf star or the cool methane lakes of Titan, it would suggest new pathways and mechanisms of evolution, expanding the scope of evolutionary theory. From a philosophical point of view, confirmation of the existence of extraterrestrial life would challenge long-held views about humanity's place in the universe. The Copernican principle, which asserts that the Earth is not the center of the universe, will take on even greater significance if we assume that life is ubiquitous rather than an earthbound anomaly. This paradigm shift may affect philosophical discussions about the uniqueness of human life, our ethical responsibility to other life forms, and our role in a larger, perhaps teeming cosmic ecosystem. Theologically, the discovery could lead to a rethinking of religious doctrines and texts, especially those dealing with the uniqueness of human life and the concept of creation. Different religions may integrate these new findings into their worldviews in different ways. It could potentially lead to a richer and more nuanced understanding of the spirituality that encompasses a universe filled with life. In terms of scientific methodology, The discovery of extraterrestrial life will emphasize the power and importance of interdisciplinary research that integrates astronomy, chemistry, biology, ecology, and other fields. This will require the development of new scientific tools and methods to detect, analyze, and understand life forms with potentially unfamiliar anatomy and biochemistry. This technological and methodological innovation may have spin-off benefits for other scientific fields and disciplines. From a societal and cultural perspective, discovery can foster a new sense of unity and purpose. Humanity may come to realize itself as part of a larger cosmic family, prompting global cooperation in scientific, ecological, and research endeavors. It could also awaken scientific curiosity and inspiration, similar to the excitement and wonder of the Apollo moon landing, but on an even larger scale. Economically, such a discovery could stimulate investment in space exploration, biotechnology, and related industries, leading to technological advances and new market opportunities. The desire to explore, understand, and perhaps even connect with extraterrestrial life could be a major driver of innovation and economic growth. The discovery of extraterrestrial life will have a transformative impact on our understanding of life on Earth, changing scientific paradigms, philosophical views, theological beliefs, and societal values. This will confirm that life is a fundamental cosmic phenomenon, prompting humanity to rethink its place in the universe and its relationship with other life forms, potentially leading to a more cohesive and enlightened global community.